Okay, it's my very great pleasure to welcome you to this UK Catalysis webinar, which will be given by Dr Monik Panchal from Durham University, who's going to talk about understanding lab-based X-ray absorption and its uses in catalysis. If you could use the Q&A box for any questions, and we will read them out at the end. If there's anything else you'd like to introduce yourself, please use the chat. Thank you very much. Hand over to you, Monik.
Perfect. Let me just quickly share the screen. There we go. Cool. So, hi, my name's Monik. I am the technical manager here at Durham in the Durham X-ray Absorption facility. So today I'm going to give a talk about lab-based X-ray absorption spectroscopy and how the application is to catalysis. So a little bit of an overview of the topic of the experiment. Sorry, something's going on there. A little bit of an overview of the actual content of it. So I'll be just about the history behind lab-based XAS, some of the advancements that have been made to get it to the levels that it is, and primarily going over what we do here at Durham itself, and specifically looking at the in situ side of stuff. And leading on to some of the considerations that we have and that we have found when doing in situ and operando studies here. So I'm not entirely sure what the demographic of the audience is, but I'll give a brief overview of X-ray absorption spectroscopy. It's a technique looking at absorption coefficients of materials, understanding the local geometry and electronics of a specific element of interest. This is the fine structure that we tend to look at, which can be expressed into two different domains, including Zane, so that's the near edge, so near the absorption edge, which is highly sensitive to the electronics of the structure, including oxidation state symmetries. Whereas if you go further along, is the EasyXAFS, which is quintessentially how the emitted photoelectron that we produce during these absorption events interacts with neighboring atoms, which can give us telltale information about coordination environments of the system, including distribution of elements around our particle of interest. So this is a very useful technique, which has been used for many years in the catalysis community, mainly because of its got elemental specificity. Sorry, I can't even say the word. It's very element specific as we attune it with a particular incident photon electron energy. It's non-destructive, which is quite useful in terms of scanning elements in a particular sample environment that you want to see. Now, depending on how we understand the technique, we can look at bulk scale analysis of a system, so it can give you a good average overview of it, and you can use other instruments with different specifications where we can improve the spatial resolution that we're able to achieve. Though it's not perfect, and there are some experimental considerations that you need to make, especially if you have worked at synchrotron, some of these and done synchrotron experiments. Some of these aspects you need to keep in mind whilst making the experiment. So it's not just about the element of interest. Other elements in the material that you're looking at can play a role in terms of how much X-rays can be absorbed, and will that impact the actual spectra that you received afterwards. Again, resolution can be a critical thing if you're looking at a bulk scale analysis versus a high result ones if you want to see individual particles. Sometimes this can be averaged out, and again, depending on the instrument at hand, certain experiments can be done, certain experiments can't be done. So there's a lot of back and forth communication with beamline scientists, and also addressing the question that you want to answer using X-ray absorption spectroscopy. So very brief rundown of that. I guess when it comes to this, it didn't actually start all at synchrotron. The first reported fine structures were in the 1920s by Hugh Frick and Gustav Hertz, but it slowly and surely got refined as we went on. As we went on through the years, so within the 70s and the 80s, um, first generation synchrotrons were available. We with their high brilliance collimated beams, they proved to be quite an excellent source to do absorption spectroscopy experiments. But as we go later into the 2000s, lab-based studies have a somewhat of a resurgence. So that was primarily due to improvements in the instrumentation specifications, including monochromators, detectors, and also a increase in demand for performing studies within a lab-based environment, which has probably led on to what we do here at Durham. So if you guys are not aware, here is a lovely picture of diamond light source here. You can see it's quite a big building. Typically what we do with the lab-based one, here's one example of a lab-based instrument, the EasyXAFS 300 Plus, which you have here at Durham. I'll explain that a little bit later on. So we'll be talking about how we can essentially do certain beamline experiments, which you routinely do at the synchrotron, and how it can be done and why it can be done to a similar sort of degree here at using a lab-based X-ray source. The first thing is the optics. They work slightly differently. With many of you familiar with synchrotron work, you might be aware about how with absorption spectroscopy, it's a magnitude of electromagnets, monochromators to essentially fine tune your beam and increase brilliance. They're focusing onto your sample of interest. Now, this works really well. Collimated beams, which you can form from the synchrotron, work really well with flat monochromators and stuff. But with a lab-based instrument, we typically use a typical X-ray source that you use for XRD, for example. So it's quite a broad range, a broad source. So what we need to do is start considering the actual optics of the monochromators and the crystals that we use, which are slightly different to what most people are aware of from the synchrotron. So from the instruments that have already been are available currently, essentially they go via two pathways, I would say. So instruments use a Johansen or a Johann roll circle configuration. These are typically used to essentially improve the focus of the incoming beam. So as a spread beam gets onto the crystal, the reflections can derail. Typically, in the early 70s, this was a Johann setup, but upon improvements in engineering, what you find is when you increase the curvature of the crystal here at the if you increase the curvature of the crystal here, what we find is that the angle of reflection can actually equal the angle of incidence coming in, so beam in, beam out, which actually improves the focal point of it. Typically, this is good. It means that resolutions using this sort of crystalline setup are quite high. We talk, relatively speaking, we're talking between 0.1 and 0.7 EVs per step. However, is a lot of moving components involved in these sort of setups. So the other instrumentations out there use a different sort of crystalline setup, which is called von Hamus one. Essentially, rather than using a single monochromator here, is a cylindrically bent crystal at the side where essentially we can fire, and we fire in a multitude of photoelectric light at the front, and we position our detector there so it can collect everything simultaneously. So therefore, a broad range of the energy range can be captured at once, which is really good for fast time resolution experiments. However, you do the compromise is resolution. So when deciding on lab-based what sort of optics you want to go for, this is something to consider, especially with the experiments that you get. Now, I'll be focusing more on the Johansen sort of crystals. This is typically what we use at the facility here. The other considerations when making it is the movement of the incident X-ray beam on a detector. So with the system from EasyXAFS in general is what I'm going to focus on here, where what we see is that we have a fixed source, so the X-ray source does not move, and in order to reflect a certain incident beam out towards our samples, we essentially move our detector in tandem with moving the spherically bent crystal analyzers here. So they are typically of a certain Miller indices, depending on what element we want to look at and what diffraction we want to see out. And some certain considerations need to be made when deciding on what crystals want to be looked at. So when selecting these crystals, essentially HKA pearls, HEL indices of the crystals need to be made into consideration. So typically the materials that we use are silicon and germanium, which are the standards, which are normally from the crystals that are made. Now, we also need to consider what happens when using a particular crystal. For higher resolution reflections, we typically go for a higher Bragg angle. This is due to how the optics of a Johansen system works. As we increase the reflection angle, the energy resolution actually drops quite significantly. So in order to do that, we typically, in order to keep that high resolution, we typically need to keep a variety of spherically bent crystals available. Another thing to consider with lower index crystals, they probably cover a lot. They can probably cover a lot more elements of interest due to reflections. However, a lot of it is considering the harmonic collision, so emissions via certain materials used in the instrument configuration can play a role in what the detector captures, and that can impact what is actually collected and further analysis that you may perform. This includes artifacts that you might express in the actual in the XAS spectra, which you need to consider, or if it will be in regions of interest that you'll be further analyzing. Okay, so I did focus a lot on the EasyXAFS, but however, it isn't the only system out there now. There are actually a couple of others, industry available ones. Now, X-ray is a company that use a similar sort of instrumentation to the EasyXAFS. However, their primary focus is using a single crystal, a single analyzing crystal, and at a low diffraction angle. So you typically don't need to change it out and as frequently as you would do with the EasyXAFS. And typically, and this can collect in both using different detectors to collect transmission and fluorescence. So von Hamus arrangements, HISA, so a company in Germany, actually focus on performing systems like that. However, these are great, especially if you are making you have especially if you are making particular cells and you want to do a faster rate of collection. However, there is a compromise in terms of resolution in that sense. And again, the EasyXAFS 300 Plus, which is an instrument, the top of the line for EasyXAFS. And again, as I explained a little bit earlier, using a spherical event crystal analyzer and using a silicon drift detector to capture the the incident and the external photon counts. Now, hopefully that's given a little bit of an overview about lab-based XAS and where it is currently is. So in the UK right now, we're Durham University has a essentially a grant where we have developed a facility here, so Durham X-ray Absorption Facility. The main people, including myself, which is happy face here at the bottom. Also the main academic lead is Dr. Simon Beaumont. He's associate professor here at Durham University. Has many years of experience with X-ray techniques, especially absorption spectroscopy and XPS. So the history behind how we all started here was roughly around 2018, where attempts were made to apply for funding to get a lab-based equipment, and toing and froing, this got accepted in 2021, where the instrument was primarily designed with the unique aspect of looking at catalysts and energy materials under operating conditions. So this is how we designed the facility in itself. And then by August 22, essentially is when I arrived, and where I do my regular day-to-day runnings of the facility and meeting with clients and customers and tackling how we can improve XAS, especially for in situ characterizations. It's actually quite a nice one here. This is the instrument coming down, so it can fit in the back of a lorry, so it's always quite nice compared to a whole beamline hutch there. And also we are able to some nice little figure of us collecting the first spectra present there. So the facility itself has essentially three main workhorses, where we have the EasyXAFS 300 Plus, which we'll go into a lot more detail, and including a catalytic reactor setup. So we use the Haydn catalytic microreactor, including MSc units, so we can understand. We can also do some catalytic studies. These are all connected in tandem, so we can quintessentially pass a gas feed through the CatLab system through the MFC units and into our EasyXAFS unit, where we can do further in situ XAS studies. The outlets that we have to monitor the outlet gases we have is a hydrogen mass spectrometer here. And again, some of the specifications here at Durham is that our EasyXAFS system can do absorption fine structure. On top of that, it's capable of doing emission spectroscopy. Now, a typical energy range that we can achieve is listed here, and we'll go into a little bit more detail about the reasoning selecting certain specifications here. And again, with our Haydn units, we've got a bank of 8 mass flow controller units, so we can pump various gas feeds through. And again, we've got quite a fast response quadrupolar mass spec, where response times are less than 500 milliseconds, which make it quite applicable when doing operando studies. And again, we have the presence of a vapor generator, which are able to pass water or other volatiles through the system. I'll give you an example of what we've done with that previously. So again, we do a lot of absorption spectroscopy, but a lot of the highlight is that the bit of kit is capable of doing emission spectroscopy. So if you're not familiar with that, it's essentially high resolution fluorescence, where we can start studying the essentially ligand to core interactions, including valence to core systems, which you not necessarily see when doing standard fluorescence, which tell you a lot of information about what is bound to your metal of interest or your element of interest. Whereas with so it's quite complementary to how absorption spectroscopy works. Yeah. So again, how we tend to use the equipment is we do a lot of ex situ work in terms of ex situ XCS. We also have the main which we're talking about is the in situ side of it. And again, with the catalyst testing, we also have capabilities of doing absorption studies here at the facility. Now, our elements of interest that we can traditionally look at using our EasyXAFS system right now is between 5 and 20, 5 and 18, 5 and 20 keVs. Now, what that covers is essentially what we see here. So in K-edge terms, it's covering the early rod transition metals, and in terms of the L edges, we start beginning with the late blocks, the later elements, including the actinides and the lanthanides. So the instrument itself covers quite a wide range of systems, which a lot of the catalysis community are interested in exploring materials with these elements present. With our systems currently is under transmission mode. We've gotten results from greater than 1% weight loading. We've been able to get usable data from that sense. And also we are capable of doing fluorescent studies in the system. Again, this will be based on a point of inquiry and depending on the system. With the research question which the user requires. Okay, so here's a nice little overview of a little video of how the instrument looks on the top. So we have our solid state detector here with our fixed X-ray source planted here. This is for absorption. When we want the emission, we essentially swap the sources between this one and this one. So you can't do them simultaneously, but this will work in that sense. What we do is fire across the X-rays to our spherical event crystal analyzer. And again, these move in tandem to our sample located in front of our solid state detector. Now, as we continue, if the animation wants to work, there we go. As the instrument moves across, the actual the beam shape varies. This is just a result of the optics used when designing the EasyXAFS. But hopefully we have a stray. The typical beam size is 1 millimeter, and the strays at higher Bragg angles. So typically when we're doing experiments, we like to keep it at the higher Bragg angles at the front here. Yeah, so in order to make sure we are able to capture as many elements as possible with the highest resolution, the facility itself has quite a few spherical bent crystal analyzers. These are typically quite expensive, but what we have done is look at what elements of interest are with the catalysis community when designing on these. So we have quite a high order of silicon and germanium crystals, which are able to achieve, for the majority of the systems described early in the periodic table, are able to achieve the higher resolution at the higher Bragg angles, which most of our users are wanting, especially when understanding features and designs on the EasyXAFS having the higher resolution. I'll go briefly over the ex situ stuff before we begin with the in situ work. So how we typically do it here at the facility, we have a multitude of sample holders which you can use to mount mount various pellets and capillaries. If you are familiar with X-ray absorption spectroscopy at a beam line, you might be familiar with 13mm pellets, pellet discs. Here we have a standalone high throughput system where it involves looking at around 7 samples. Typically, when we do these analysis, especially with the high throughput system, we want to put a reference material present there in terms of similar to how we have reference materials when doing synchrotron work, just for calibration purposes. And also, unlike the synchrotron where the background emissions are typically collected prior through the ionic chambers that are used, we are unable to do that. So we have an extra slot where is used to essentially as a blank, so we can use that to capture the I0 during the experiment, which can be normalized out to get our spectra afterwards. So in terms of, relatively speaking, compared to synchrotron work, lab-based XAS does take longer to acquire the data. Typically for a Zane scan, it's roughly around 15-16 minutes, and double for an EasyXAFS to K to the 12 in terms of the range. And again, multiple scans need to be taken, so we get the best signal to noise for the spectra. But we can vary these parameters. Again, this is one example where we have slightly changed the step sizes that we use. So these are between particular energy ranges, and this has allowed us to focus on particular areas of the particular regions of interest on the ZAS spectra that we get. And yeah, so here's some of the examples of the spectra here. So we can typically at the 16-minute mark, we can get a spectra, but however, we are able to get usable spectras within the 2 to 4 minute mark, which is quite useful, especially when wanting to perform in situ work and faster time resolution. We're able to see what our elements of interest are doing here. This is also done for a one weight loading nickel and alumina standard that we have here, which hopefully conveys the actual spectral quality they can get with relatively low weight loadings of materials in the system. Now, again, here's another example of how we can actually alter the setup. Again, with the step, a lot of people are interested in the absorption edge region, especially when looking at the Zanes. So sometimes getting high resolution there can improve the visualization of pre-edge features which you might have on the system here. So taking the same sample, we can actually improve the step the counts within the absorption edge region. And typically this, even at 1 EV, is typically quite useful. But also you're able to go down to 0.1 EV of a step, which is seen quite prominence with a lot of our users wanting to study the pre-edge features. Again, we don't need to have a pellet. We are able to design essentially a reactor holder for capillary cells. Now this has, in terms of optics, has a few more criteria that need to be fulfilled when doing it. Now, typically our beam size is 1 millimeter in terms of diameter. So the capillaries that we use, we tend to not use capillaries smaller than 1 millimeter in terms of their internal diameters, just to avoid stray X-rays passing through, which can affect further the other idea is with with doing capillaries, we use a aperture in front of it, which might reduce the counts, but also improves the focus of the absorption that we see coming through. As a facility, we got capillaries available, which are standard ones, which are used for XRD and borosilicate, borosilicate, quartz, Captain, and and other materials. As long the thing we need to consider is the attenuation, depending on how much metal loading or elemental loading that is present there. Okay, so now I want to go on to some of the work that we've done with in situ, which how we designed out the cell was we heterogeneous over a solid heterogeneous catalyst over a gas feed with very varying temperatures. So we designed a cell here, which is used to achieve this. Mark one here. Now, our main primary uses have so far been users wanting to do TPR studies and understand the oxidation of the catalyst, and standard ROR experiments. But hopefully, I'll be showing you some of the work that we have done with the TPR side of it and the ROR, and leading on to how we've used it in tandem with hydration, other techniques, including introducing water into our systems. Yeah. A little bit more of the specifications of this cell. It's primarily designed to go to roughly around 400 degrees. Now, this is something that is being looked at further to improve the temperature range that we can achieve. And again, the actual pellet cell itself, the actual pellet temperature itself roughly follows the temperature of the cell. The initial design has been for a 13mm pellet. However, we're able to use smaller pellets in this system successfully, using various apertures to achieve this. So one of the major works that's been going on with the facility is with the Beaumont Group here at Durham, looking at peripheral hydrogenation as a system. So the main requirements were we want to understand how potentially two different pathways of peripheral hydrogenation can lead to different products depending on the region of the metal species, the region located in the system. So Szechuan here has primarily worked on this through her PhD work. This involved designing catalyst systems where copper is been specifically tailored to be inside or outside porous silicate shells. Now, what was the research question that wanted to be asked was, is the reducibility of the copper different between different locations in the system, and what copper species dominate around the reduction temperatures? So how we achieved this was performing a multitude of in situ works on various materials that were prepared with inside and outside copper species, and we wanted to see the change in the speciation using copper KH-Zanes. We did some further analysis using linear combination fitting, which is primarily some well-resolved standard spectra to work out the proportions of copper within the system. Prior to the work, we actually performed some ex situ studies before and after reaction, so we can gauge what the material is meant to look like. And also with this, we also performed some TPR work within the cell itself, just to study when we start seeing the reduction process through the mass spec. Now, here are some of the results which were prepared. It has been relatively successful when identifying how different copper species have been formed throughout the experiment. Again, at the reduction temperature is roughly seen around about 200 degrees when we are performing these. However, we start seeing a transition occur as early as 160 in this case. In this case of this copper system here, where you have the formation of copper 1 species and copper metal happening simultaneously. However, with another material present, you can actually see that the copper 1 species occurs a little bit earlier compared to the formation of the copper foil. Okay, so this result has actually helped the user understand the reaction pathways present in her system right now, and further along understanding the research question, which she was evaluating for her PhD work. So it was nice and successful. Other works that we've done is looking at other industry relevant reactions, including Fischer-Tropsch. So unfortunately, we can't go to high pressures in the system here, but one of the projects which we are looking at here at Durham was how bimetallic systems and individual cobalt-containing systems, how the spillover effect can vary between monometallic and bimetallic species. So again, we conducted a lot of reduction series here, working out the isothermal points and determining how the reducibility of cobalt is between a monometallic and a bimetallic system. So what was found here is that there is probably quite a standard thing with the literature, that presence of platinum in the system causes a significant drop in the reducibility of the cobalt species, occurring as early as 275 degrees in this case, compared to how with the monometallic species we actually do not see any evidence of significant reduction, even up until 400 degrees. So it's quite a interesting phase. Again, linear combination fitting was done with these systems, and it found that it went for a transition of cobalt 3 to cobalt 2 to cobalt metal. And again, at the what was useful is that at the end we found that the cobalt species wasn't too reduced. And again, looking at a mixture found with linear combination fitting of a mixture of cobalt oxide and cobalt metal present there. Now with the same system, we continued the cycles, and we want the idea that the user wanted to see was what's the effect of water, and again with Fischer-Tropsch especially, the presence of water can cause an impact. So how we performed this was using our vaporizer. We passed through a significant amount of water through the system, and what we saw with a variation and increase in temperature is that a total change in the cobalt species, which was present after hydration. So for the user itself, this helped with the further analysis that they performed with the system. Now, there's been a lot of work done with the in situ work at this lab-based setup, but there's a lot of different considerations that you may need to make when performing these experiments, especially in a lab-based setup. So hopefully the next few slides, I'm going to be going over some of the criterias which I found when conducting these sort of experiments. Firstly, it's the footprint on the space when designing your reactor. Now, this is an image that I had on one of the earlier slides. However, the actual footprint of where our reactor can go has to sit within a region roughly around about this size. This mainly is a consideration of how our instrument works. There are a lot of moving components in the system, and how the X-rays are actually enclosed. The foot space, we're talking, like 60, 70 centimeters close to our helium path present there. This is can make some significant engineering questions to be evaluated when making temperature cells and electrochemical cells, or especially including where our where the actual reactor cell, and including any external equipment, needs to be placed in order to not impact how the actual optics and the motorized system works here. The second consideration is, I'll say, knowing what question you want to answer with lab-based XAS, and can this setup achieve this? So what I mean by this is that is there a correct pseudo monochromator present as a which can achieve the correct EasyXAFS range that you need? Can it go far into our Bragg angles without obviously losing resolution or having impacts from different harmonic collisions, which you might expect, and could impact the data quality that is achieved out. Now, another thing is monitoring the products formed. We have quite a high speed, high resolving mass spec present at our vent, the outlet of the reactor, and again, potentially GC setups can be made there. However, it needs to be considered that with the time of acquisition cannot be correlated with the absorption spectra that you collect. And again, this is sometimes these spectra take a long time to acquire, 16 minutes, which can impact on what questions that can actually be answered using lab-based XAS. A good way of understanding also is the data quality that you may achieve. So very much recommended screening the sample under the gas conditions just to achieve just to see how the actual the signal to noise of the data, how does that perform in the instrument, and will it answer the question that you are wanting to see? Another consideration to be made is considerations when deciding on, especially with in situ work, how long your isothermal points are meant to be, and how will that impact, especially kinetic and thermodynamics. Again, we want to capture as many scans as possible to improve our signal to noise. However, if this means that our isothermal points are hours long and cannot answer the question that we have on hand, we need to consider this when making the experimental setup for the system. And again, this can be overcome by other analytical techniques done prior to the experiment, similar to how we have a beamline. The more information that we have, the more tailored the experiment can be. And a similar thing with the lab-based XAS. So typically doing, let's say if there's a reduction, typically doing TPR experiments just to study what is going on, is a good example of, prior to experiment, is a good example of helping work out how our experiment is set up. Now, a couple more things, 4 and 5. Backgrounding, we found, is a significant part of delivering high quality spectrum here. So our backgrounding again is done with a separate I0 sample. So this is typically done with the in situ setup prior to the experiment, under a certain gas feed, and also done near to the end of it. any drift that we see is normally tracked by standard emissions that are emitted out, and we follow them along. But adequate time does need to be made when performing these experiments for conducting successful backgrounding, and also conducting the XAS for any reference materials present there. Now, again, this the technique, especially with the in situ work, when we start going to lower Bragg angles, resolution, and beam alignments become a significant factor. Now, when we what we found is that spending a little bit more time prior to experimental experiment starting, improving, doing more improvements in calibrations and alignments of the instrument can lead to a significant reduction in artifact emission intensities, which can lead to reduction in these artifacts or total emission in further process spectra that you get. Okay, so hopefully this is giving you a little bit of an overview about how lab-based, especially with in situ work, is performed here at Durham, and how we can potentially do other experiments here. So what we normally do is we have, if you are wanting to submit in samples here, we basically have a certain procedure that we follow. The first primary point of call is contacting the facility itself. So that can either be me or Simon, or we have a general email feed, which I'll be showing the details at, in the later slide. What we do here at the facility is, once we discuss about your sample and experiments that we want to consider, and we are happy with what we want to do, we have a submission form, which is found on our website, which is easily filled out, and again, writing down the requirements that are requirements for the experiment that wants to be set up. Now, again, with working in our facilities, we like to have the SOP's risk assessments present with us when we are submitting samples. So do bear that in mind, especially when you're submitting samples to us. Typically, I do like putting 2 to 4 weeks on here. I think a lot of ex situ work does. The results are back as sooner than that in most cases. But again, it's the demand on the instrument and how long it takes. Again, with in situ work, this can obviously take longer, and especially if there is a long-term project which is wanted to be explored. This needs to be fitting with the schedule of how our equipment is being used. Yeah, so we have some, again, further information here. We've got general inquiries and a couple of mine or Simon's email addresses. So if you're interested in doing the lab-based XAS systems, please do get in contact. We do have a website here at Durham, which can tell us more information, and we have a newsletter which is bi-monthly and usually gives an update about how the facility is doing and what achievements have been made from different users. They're happy to talk about it. But yeah, so it's not so. I'd like to thank quite a few people here. Again, quite a few people here from Durham. We got a great technical. We got a great technician workshop team here at Durham, which have helped significantly in the design, the fabrication, and the setting up the electronics for the in situ cell. Again, having this option here, we are further looking at exploring different types of in situ and operando cells for our community. So if there's any experimental questions you're interested in following up on, and the cell in its current entity doesn't fulfill it, please do get in touch, and we can discuss about potential design of cells or consideration in further iterations of it. Again, there are also quite a few people from Diamond and UCL and which I haven't mentioned in terms of collaborations and points of contact when discussing lab-based XCS, and also the EasyXAFS itself. The company has been quite helpful in help in the development of the facility itself. So that is me. So I'm glad. Thank you for listening, and I'm happy to take any questions.
Thanks, Monik, for a really comprehensive and clear talk. We've had a couple of questions come in, so we'll read them before I take share. So the first question is, what sort of concentrations and collection times are you using for valence to core measurements?
So typically what the facility hasn't actually got too many valence XES samples come in for it, and this is something that we really want to explore in terms of especially with working out collection times and stuff. On a standard with the XES experiments is they take roughly 5 minutes, but it's depending on the data quality that we're getting out from it. Again, it's the more spectra we get out from, the averaging counts improve in it. So however, we haven't really got too many examples of it currently. So if the person's interested in looking into exploring it, by all means get in contact and we can tackle it like that.
So the next question from Luke is, does the capillary cell do heating or just the pellet cell? And what sort of, there's 3 questions, so I'll go through them one at a time. So yeah, so does the capillary cell do heating? The
capillary cell does not do heating in its current state. However, this is something that's definitely being explored with the facility right now. I think the main caveat which we're finding again is the engineering of it. We've got a relatively small footprint. However, so a lot of consideration, especially in terms of temperature ranges and stuff, need to be we are currently making. So it's designed for our user base. Yeah.
So Ivan, sorry, is asked to submit samples. Will you accept samples from other countries, or is it just UK?
No, I think there's no issues with accepting other samples from other countries, provided the institute is happy to discuss about quotations and stuff. That's all fine. And obviously, if the samples are able to get into the country, that's another consideration. So yeah, so no, but by all means, if there is anything, do get in touch, and if there are any issues in terms of logistics with other countries, we can always explore that further.
So the next question is about data. Is the data from your lab compatible with beamline data? This is, can you, for instance, measure additional standards in the lab and then use them, for instance, in fitting the beamline results?
So yeah, so far we haven't had too many issues with comparison between beamline data and or the data which we get from the labs. Again, it's all about data quality. It's both ways. If the data quality is, if the sample is the data quality that we get from the lab-based X-rays or the synchrotron is quite noisy, it can impact how we have the comparisons with it. But certainly with the linear combination fitting, some users have just used synchrotron data collected and when as the reference standards, and they haven't seen any issues when using them for the statistical analysis.
Okay. And then what formats of data are produced by the DXF?
I'm sorry, can you?
What formats of the data are produced by the
yeah, so from we typically send out the data. It can be sent out as a .csv, but again, with further processing, we actually do put it onto Athena or any Demeter package there. So it can be used just as simply as synchrotron radiation data that we get.
Okay. Might be interesting. So we've done some work with STFC on producing workflows for analyzing XFS data off the beam
Hmm.
lines, and that's now a published workflow. It might be interesting to see how that works. This is my ignorance completely of data and Athena, but it might be interesting to see if it's compatible.
Oh yeah,
Uh,
definitely. Yeah, I'm guessing it'll just be worst case scenario. It'll be just putting a slide in the script, being like, oh, read.csv. But we'll yeah, no, that'll be very interesting to see how the automations how it can be used for the lab-based setups.
okay. My quick question. The first question was so where sort of diamond obviously has a history of cells and environments.
Mhm.
Obviously, there's completely different engineering criteria for the lab XFs.
Yes.
But can you take what they've done and modify it, or is it starting from zero and completely redesigning?
Oh yes, 100%. I think um, a lot of the time the actual optics themselves, bar the actual optics of getting the as long as we get the X-rays to the sample and to our detector, that are the main criterias, I guess. Um, Now, with terms of the cell design, depending on the cell, again, if it's does it fit in the system itself? How are the windows and the mirrors set up? Does it need anything? Does it need anything in terms of in place with the detector, with the actual setup, which can it be, will it come in the way of any of the motions that we see, which is also a big consideration with it. But yeah, no, I think the majority of the time you can definitely use it as a blueprint, especially when designing setups.
Okay. And then the other sort of question I had was a bit more administrative.
Mhm.
If someone's been doing diamond XAFs and wants to use sort of the easy XAFs or
Yep,
the lab XAFs,
yep.
what would be the one piece of advice you'd give them, other than those lovely criteria that you explained very clearly? Is there anything you'd say to people to really think about?
Um, if apart from the criteria is um I guess I think it's I was gonna say the actual experiment that you want to uh the experiment and the question you want to answer, I think, is the main thing. Quite a
Okay.
lot of if you're looking for really long range exercise, on a lab based setup, you really need to consider if it is feasible. Now, if you have your setup and it can start at a high Bragg angle, yeah, bam, we can go to like K 20, 25, potentially, depending on the material that you look at. But
Yeah.
also it's yeah, I think it's mainly the experiment setup. I think also understanding that it does take longer than actual standard synchrotron data that we get, which can play an impact in, especially with the in situ work, play an impact in, are you actually answering the question that you are wanting to answer due to just collection times. Yeah.
Okay. Do you have any issues with things like beam damage? I mean, obviously it's
No.
lower intensity, but there's longer times.
Yeah, so far with how we've done with the ISO what we haven't seen any evidence of significant beam damage in the systems there. But also this is within the timeframes of a user's requirements. I guess if we just fire it across on the same sample and energy for like 3 days, it may be, but this is typically not a requirement for the requirement time frame for the user. So yeah, it's been okay for that.
Okay. I am just running away with my questions here. If
No,
anybody has any more questions, I'll ask one more, so you've got time to quickly type one in. But if someone hasn't done any XAFs ever,
yep.
would your advice be to come and talk to you?
Yep. So we can traditionally what we've been doing, especially with people in the local area, is getting in contact and actually going through them in terms of the data processing, process side of things.
Okay.
Um, again, pointing them to if they are further away, obviously get in contact and pointing them to other resources available, especially down at Diamond, and even the resources available externally, internationally.
Okay. Well, no more questions have come in, so all that leaves me to do is to thank you, one, for being perfectly to time, and two, for a very excellent talk. And hopefully you see lots of catalytic people in Durham soon.
Yeah, by all means, get everyone get in touch. We're still here. We're still churning away. So yeah, well, thank you so much for having me.
Thank you. So thanks everyone for joining. I'm going to close the webinar now, and I hope to see you at a future Hub webinar very soon.
Thank you.
Thanks
Bye.
again, Monik.
Thanks, everyone.
Bye.
Bye.